Once upon a night of tension across the dark skies over conflict zones, something unexpected happened. A sophisticated Russian cruise missile, one meant to slip past defenses, was felled not by another $1 million interceptor, but by a relatively low-cost, laser-guided rocket. The video evidence spread like wildfire. Putin erupted in fury. Today we're diving into how Ukraine managed to strike that stealth missile using cheap tech, and what it means for future warfare. Hello everyone, welcome back to the Strikepoint Media channel. Please subscribe and like my videos. When you hear stealth missile, you imagine top-tier engineering, radar evading coatings, advanced guidance systems, multi-million-dollar procurement. That's exactly what Russia wants you to think, that their Cage-type cruise missile, often reported as Cage-69 or variant, is untouchable, unstoppable. But overnight, the narrative cracked. Analysts and open-source investigators have confirmed that a Ukrainian air defense unit used a laser-guided advanced precision kill weapon system APKWS rocket, costing perhaps tens of thousands rather than millions, to intercept the missile mid-flight. Imagine the headlines: Russia's stealth missile shot down by cheap tech. Putin's fury is not just about a failed strike, it's about the perception of military dominance unraveling. In today's breakdown, we'll walk through what made that possible, the pros and limitations, and what this tells us about modern air defense. So let's get into it. Let's first consider the exterior, the outer characteristics of both the Russian missile and the Ukrainian intercept system. From what is known, Russia's stealth cruise missile, allegedly Cage-69 or updated variant, is designed to minimize radar cross-section, fly low, use terrain masking, and approach targets with reduced signature. Its fuselage likely includes radar, absorbing materials or shapes, careful design of control surfaces, and internal compartments to reduce plumbing or external protrusions. It's built to evade conventional radar and air defense systems, to slip through gaps in layered defenses. On the Ukrainian intercept side, the external shell is deceptively simple. The APKWS rocket is essentially a 70mm Hydra family rocket upgraded with a semi-active laser seeker and guidance kit. The body is still that compact 70mm tube with fin assembly, not bulky nor expensive. It is fitted into existing launch systems or SAM platforms like the Vampire/BRAWLR air defense launcher. That low-cost modular retrofit nature is crucial. You don't need a bespoke, expensive interceptor. You can adapt hard, where you already have, attach a laser guidance kit, and repurpose it for high-end threats. So externally, you have a high-end missile trying to hide and a low-cost rocket cunningly upgraded to hunt it down. That juxtaposition is already a story in contrast. Expensive stealth vs. cheap precision. Now let's move to the interior. What's inside these systems that makes them tick? Inside the Russian missile is a complex suite: inertial navigation, possibly terrain correction algorithms, radar altimeter or height sensors, a small propulsion engine turbojet or small jet, warhead payload, and control actuators. There may also be signal processing, guidance corrections, inertial measurement units, and possibly countermeasures, chaff, decoys to defeat defenses. All that tech is expensive, requires precision manufacture, calibration, and materials capable of withstanding high stresses and temperature. It's also vulnerable. Sensors must trust incoming input, and guidance algorithms can be tricked or spoofed. The missile's interior systems must balance between stealth, weight, power consumption, and reliability. On the intercept rocket side, the interior is much more austere. The base rocket motor, propellant charge, control surfaces, a laser seeker, electronics for guidance, actuators to steer fins, and necessary wiring. The laser seeker is semi-active. It homes in on a laser reflection pointed at the incoming missile. Because it doesn't need a full radar seeker or a large propulsion module, cost and complexity are lower. The guidance electronics are simpler, especially because the target is illuminated by laser and the path deviations are limited. The trick is in coordination. You must keep the laser spot on the missile, which means a targeting system, ground or air, must track and designate. When all parts sync, that low-cost rocket becomes a precision interceptor. This contrast is essential. You don't need utter complexity to strike something that seems complex, as long as your solution is clever and coordinated. Now let's shift to performance. How well does this cheap tech intercept work? What are the metrics? Reports suggest that during a barrage of missiles and drones, out of 4 launched Russian missiles, 1 was intercepted by this method. The speed, trajectory, and maneuverability of the stealth missile pose challenges. The APKWS rocket must match or exceed the closing speed and adjust its trajectory quickly. In tests, the intercept was successful, meaning the rocket's agility, guidance responsiveness, and timing were good enough to catch the missile mid-course. This performance is remarkable given the cost difference. Traditional surfaced, where missiles, SAMs, or dedicated interceptors cost orders of magnitude more. The interception success shows that the low-cost interceptor has acceptable range, speed, and guidance precision when conditions are favorable. However, performance limits exist. These rockets have limited range and maneuvering margin. They are best deployed when the target is within line of sight and when the laser can maintain lock. In dense electronic warfare environments or with stealth countermeasures, the guidance may fail. The intercept window is narrow, timing is critical. Also, weather conditions, atmospheric effects on laser propagation, obscurants like dust or smoke can reduce effectiveness. Next, safety features. In a military context, safety means reliability, fail-safes, minimal collateral risk, and avoidance of friendly fire or unintended detonation. For the Russian missile, safety features internally might include self-destruct if it veers off, guidance fail-safes, encryption to resist jamming or spoofing, protections against overheat or structural stress, and internal diagnostics to abort if something fails. For the Ukrainian intercept system, safety features include safe arming distances, guidance cutoff if track is lost, safe detonation logic, and possibly self-destruct if it misses or drifts away. The laser seeker system may be designed to avoid locking false objects or friendly assets. Since this is a retrofit system, integration into existing command and control ensures that engagement rules and identification friend-or-foe systems reduce risk of misfiring at non-hostile objects. One interesting safety aspect is cost. Because the interceptor is low cost, the risk of waste is less severe. Losing one rocket is far less damaging financially than losing $1 million missile. That flexibility adds to operational safety. Commanders can take shots without extreme risk of resource loss. Let's talk unique selling points, what makes this setup stand out, why it's a game changer. First, cost asymmetry. You have cheap rockets defeating high-end missiles. That undermines the Russian logic of spending big on stealth. If you can be shot down by $25,000 tech, stealth loses glamour. Second, adaptability. The system is retrofitted into existing launchers or defense systems. It doesn't require an entirely new infrastructure. That modularity means faster deployment, lower development cost, and widespread scaling. Third, scalability. Because the rockets are cheap, you can field many more interceptors. You can overwhelm the adversary's attacks by volume. Also, even if some misses occur, the cost burden is manageable. Fourth, democratization of defense. This method lowers the barrier for nations with limited defense budgets to counter more advanced threats. That shifts the strategic balance. Now missiles are vulnerable even to lower-tier opponents armed with clever tech. Fifth, psychological impact. For Russia, this is an embarrassment. Putin's credibility suffers when a supposedly advanced missile is shot down by improvised methods. The propaganda value is huge. Now, in our script, you requested price. In this case, the cost of the interceptor vs. the enemy missile. Information is partial, but credible reports say each APKWS converted rocket round may cost around $25,000. Meanwhile, Russian cruise missiles of high-end types often cost in the millions. The cost ratio is dramatic. One source used the comparison, a $25K rocket vs. a $5 million missile. So economically, Ukraine is turning high-cost missile duels into low-cost precision engagements. Even if a few intercepts fail, the balance is heavily in their favor. Putting all this together, here's what you emphasize in your conclusion. This incident isn't just a single tactical win, it signals a deeper shift. Stealth, espionage, and high-cost procurement are no longer guarantees of superiority. Clever sensor fusion, retrofitting existing munitions, low-cost precision weapons, these are leveling the playing field. In asymmetric warfare, cost-effective innovation matters. For Russia, the message is painful. Your expensive missiles may be overconfident, vulnerable, brittle. For Ukraine and allied nations, the lesson is hopeful. You don't always need to match your enemy dollar for dollar. You need ingenuity, coordination, and agile strategy. As for viewers, keep watching how this story evolves. Will Russia change missile design, add countermeasures? Will air defenses shift tactics? Will other nations adopt similar low-cost intercept methods? Those are the big questions. Thanks for watching. If you enjoyed this breakdown and want more videos that dissect cutting-edge military tech and tactics, hit subscribe, like, and drop a comment on what you want us to analyze next. See you next time on Strike Point Media.